So now we have an elevator supported by a cable, and we see these forces drawn like this. We can see they're intentionally not drawn equal, so that means there is a net force like this. For when the elevator is moving upwards during the first 0.5 seconds, and we know that's accelerating. And so that net force is what produces the observed acceleration. Now down below, we're asked to draw the free body diagrams during the following time intervals, 0.5 to 11.5. Well, 0.5 to 11.5 is that time when the velocity is constant. And if the velocity is constant, then the acceleration is 0 and the forces are balanced. So we have been given as a model the size of this weight, and we want it to be the same size as the other, Fg. And so we know that also the tension must be equal, and we want to label them. And so we even say Ft equals Fg. We want to eliminate any ambiguity about what we might be interpreting, what we're trying to say. In the second case, 11.5 to 12.0. So this is the case where it's slowing down. It's slowing down at the top. So we know Fg is going to be exactly the same size, and we want to show that, Fg constant throughout in all three free body diagrams. And so now the acceleration, it's not traveling at a constant velocity in the vertical direction. It's actually slowing down. So gravity is actually winning in this case. So we want to show that the tension is smaller than gravity. And we can even say this: the force of gravity is bigger than the force of tension. Or force of tension is less than the force of gravity. I'm going to make it unambiguous. We can even do this, put that line there, that one line there, and that one line there, omitting it from the other side. So we're showing all the forces of gravity are equal, the weights are equal, and only in this one is the tension also equal to that. Next we go on to E. And now we have a graph of weight versus time. So if we were to do an oizerga on this, the origin is 0, 0, good. The y-axis is weight, which is a force. The x-axis is time, and the intercepts. And so there's not really a curve drawn here. And so we've got W as the weight. And so what we're seeing here is a y-intercept saying that the weight, Fg, equals W at time 0. And there's no x-intercept. We can read weight in time, Fg in time. The slope is delta F over delta T. So that's the rate of change in force. And then we have the area, which is force times change in time, which is the impulse, which happens to be equal to the change in momentum. All right, so we're asked to sketch a graph to show how the reading on the scale varies during the whole 12 seconds. Well, we know at 0.5, starting at 0.5 and ending at 0.5, it's going to read normal. It's traveling at a constant velocity. So that's key there. We might even want to specify that that's what's going on there. That's discrete. Now, what we know is that the scale reads heavy when it takes off. So the weight will be higher. Now, we should draw that like this, but we know in truth, if there's shoulders we put on it, that it's not going to be a straight line. But the acceleration that we are shown in this graph given to us is constant acceleration, which means it's going to be a constant force added to the weight. And we know it's going to read light at the top. So that will be underneath as well. So we see a discontinuous function where it just drops off. Part F, we are asked to, it returns to the ground floor where it comes to rest. Describe and explain the energy changes that take place during the whole up and down journey. So what we have on the way up is we have electrical energy going into kinetic energy and gravitational potential energy while accelerating. It is getting higher, but it's also increasing its speed. And then we have electrical energy going into gravitational potential energy while at constant velocity. And then as we get higher and near the top, we have the kinetic energy and the electrical energy going into gravitational potential energy. So notice that all of this kinetic energy that was created ends up going into the gravitational potential energy. Now, it's important when we're describing this that we are accounting for this kinetic energy that was created being converted to gravitational potential energy. The work isn't being done twice. The electrical energy, the work done by the motor, is not doing the work that is being done by the kinetic energy being converted into gravitational potential energy. So then when we go downward, we have gravitational potential energy initially going into kinetic energy plus thermal energy. Thermal energy in the motor. And so this is while accelerating down. And then we have the gravitational potential energy going into electrical energy while at constant velocity. And then at the bottom, we have kinetic energy and gravitational potential energy going into thermal energy. And so this is constant, and this is accelerating at the bottom. So all the energy that went into the system initially was electrical energy that went into kinetic and potential. Then the potential went into thermal energy at the end. And that is question B9.